Hey everyone, Michael Unger here with another edition of Ask an Astronomer with our trusted astronomer Marley. We are here in the offices on the unceded territory of the Musqueam, Squamish, and the Tsleil-Waututh. A very rainy November. Marley, our last show, it felt like we were in October and it was still summer, and it suddenly switched. What's happening here?
Weather changes. Like, I don't know what's happening. Like,
I felt
it's
like as
November,
from an
it rains.
astronomical point of view, you would be like have
I'm
some
not a
knowledge for us.
meteorologist, but like, yeah, no, it's just raining now. I don't know. It's Vancouver. It's November. We're getting closer to winter time. It rains now. When
Is
I
it?
said I wanted it to be cooler, I didn't mean this. So, little whoops on my part,
You
but
wanted to be
whatever.
like cooler.
No, I wanted it to be like maybe not 20 degrees anymore.
Oh, okay. Well, what's also interesting too is that on the weekend, it's daylight saving time is ended, and I wonder, as an astronomer, if you have any thoughts about daylight saving time.
Um, as an astronomer, no. As me with a lot of opinions, yeah. It's just, I mean, it really has less to do with astronomy and more to do with agriculture more than anything, right? Like the time that the sun is out, when crops would grow, how much daylight is left, and then it kind of turned into like a working thing, like when people would work and more with that. And so personally, I do not like leaving work and having it be dark outside. That's very
Mm,
depressing because I get
okay.
here when it's dark outside. So I prefer standard time over all of it when all is said and done. It's
But
a
isn't that
better
isn't that the reverse then? Isn't standard
uh
like if we stick with standard time, wouldn't it be darker earlier
you
if we
know what? I
didn't?
don't know because I don't remember which one's which. I don't like leaving work when it's dark. I don't like coming here when it's dark. I remember having a chemistry lab when I was at UBC. I would start my day, it would be dark outside. I would go into my lab, it would still be light outside. I would leave my lab and it would be like pitch black. And that was the most
Hmm.
depressing thing ever. And so I just don't like it. I don't like having to switch time. My cat yells at me because she doesn't understand what's going on. And I
Wow.
don't like it. And that's a talk for another day because I will talk. It's so irritating.
Well, I also have opinions on it as well, and I've been reading some studies, but it is connected to us, obviously, because if it's darker earlier, the stars are out earlier,
Oh, that too. Yeah.
and you also like your brain shuts off, and maybe we need sunlight in the daytime to help us wake us up. There is some studies about this, but that is for another topic. If you are watching on YouTube or on Facebook, let us know what you would prefer. If we abolish this change, which would you prefer, daylight saving time or standard time? Some sleep researchers say that it's good to have earlier darkness. But as Marley said, maybe it's depressing to leave work and have it being dark.
Oh, how's the day
That
already
being
over?
said, we've got some space stories for you. Our big topic for today is leading into our November theme, which is cosmology. So we're going to get into quantum black holes. If you've never heard of this word quantum when it comes to space before, we're going to get into it. Sorry.
Michael, don't die on
A
me. Come
little
on.
bit of a cough there.
Pull it
Um,
together. Let's go. Yeah, quantum properties of black
but we've
holes.
also got a
Yep.
couple really cool news stories, an Artemis update, and we've got a Chinese rocket tumbling to Earth. Marley, what is happening in space?
What is happening? I ask myself every day. So the Artemis 1 rollout, here we go again. We have the first motion for the rollout. So when they bring the Artemis SLS system with the Orion capsule on top, when they roll it out of the vehicle assembly building where it's been living since it was moved from the launch pad due to Hurricane Ian, it's going to head back to the launch pad. It's going to move actually at 9:01 p.m. Our time, Pacific Daylight Time, PDT, tonight. That's when they're anticipating the first motion to happen. So when they first start moving, it moves very, very slowly. It's very big and very heavy, and they don't want to knock it over. So it moves very slowly to the launch pad for the anticipated launch on November 13th, with the window opening at 9:07 p.m. Pacific time. I guess that would be PST by then. I don't understand when this happens, but whatever. It'll be in the evening of November 13th.
Okay, and we've been hotly anticipating this, and lots of people have been talking about it. The Canadian Space Agency, obviously heavily involved. If it does launch, what's going to be really cool is that we're going to have a full dome of the launch, and we're going to put it into our shows. So if you're curious about that, and if it does launch the next day, Marley's going to put in that full dome, which will be really fun, into Surfing the Solar System, one of our shows that we do here every day. Another big news story that's been happening, breaking news. I just learned about this a couple days ago. The Chinese Space Agency, which generally doesn't send out lots of information about what's happening, but of course they are doing something. They're building a new space station. So they've been sending lots of rockets up, building the space station. And one of those rockets is tumbling back to Earth, as it has done over the last few years when they do this. And it's kind of an uncontrolled descent. So Marley, what is happening with this Chinese rocket?
So this is the third or the fourth time now that this has happened with the Chinese Space Agency. This is the same type of rocket that we've heard about. I think the most recent one is when it, or maybe not the most recent, but one of the most memorable, when it came over the Philippines and it broke apart, and we had all those videos of all of this stuff being lit up in the sky as it fell through. So this is happening again. So like Michael said, the Chinese Space Agency is building their own space station. But the rocket they used to launch pieces of that space station, the Long March 5B, the core stage, they let it uncontrolled fall back to Earth. And this like isn't super uncommon. Things have to come back down. The problem is that they have, what's happened is that they have a much wider risk that they'll take. They'll take more risk than NASA will. And so we end up getting these, kind of wild reentry predictions, of which we don't know where it's going to fall. We have, what I'm showing now is from the Aerospace Corporation, that shows all of the possible places it could fall. So that's what it's showing, the reentry path for this object. And it could fall anywhere. We don't know where it's going to fall. We have kind of a time where it could re-enter the atmosphere and fall. And that's at about November 4th. So tomorrow morning at 5 a.m., converting from UTC to Pacific time. Plus or minus 4 hours. So it could fall. Like there's a kind of an 8-hour window where this thing could actually re-enter the atmosphere and fall again. And this is like the second here we go again story, right? This has happened before. It's going to happen again. It will probably continue to happen as they, continue to build. I think they're almost done their space station. And continue to send things up there. It seems to just be something that we may just have to deal with at this point.
Okay, so watch out for that. You can probably, if you go into Twitter, usually, although Twitter is not really the best place to be going recently, but you can get some information because this could happen today. And so watch out for that later on. But our big story for today is actually, like I said, getting into our monthly theme, which is going to lead to our first 19 plus event, our Cosmic Night on November 17th, which is cosmology, but specifically quantum cosmology. And we're going to connect this to how quantum and the quantum universe, if you want to call it that, connects to black holes. So Marley, why don't you, in your best astronomer way, explain quantum black holes?
I will, in approximately 30 seconds on my computer. There it goes. Okay, so it's, oh my God. Quantum properties of black holes. Yeah, so this was fun. And I was kind of inspired about this because we're having this event coming up in the mid-November. And so I wanted to try to find a story that would kind of relate cosmology and this quantum thing that we're doing in the middle of November. So the quantum properties of black holes. So black holes, very big, very extreme gravity environments. They're predicted by the theory of general relativity by Einstein, right? That's what gives us black holes, regions of space-time from which nothing, not even light, can escape. On the other hand of astronomy, we have quantum or quantum mechanics, which is like looking at the very, very small stuff, subatomic particles, things that are very, very little. And people really want these two things to work together. We really want both these things to explain stuff and have it all work together, because sometimes it doesn't. And when you put them together, you end up getting some strange stuff. And by strange stuff, I mean things that are hard for even me to think about and frustrate me at some times. But it does get a little weird. Like if you've heard of Hawking radiation, like that's like a consequence of putting these two things together, is what you get. But the one article, the one paper I saw rather, that I was like, oh, this is very interesting, dealt with mass superposition in black holes. And this is from the University of Queensland. And the author was PhD candidate Joshua Fu and a few others, though he was the lead author and the lead of the team. And they wanted to see if a black hole can have wildly different masses at the same time. And now this is a property of quantum mechanics known as superposition, which I'll explain in just a second. But this is what they wanted to find. And basically, it was as if the way they described it as, can a black hole, it would be like someone being tall and broad and short and extremely skinny at the same time. Having all these different different masses, different properties, but simultaneously, which is a part of quantum mechanics. To do it, they did not look at black holes. That's another thing that you can't just look at it because you'll see one result of the superposition states. So they used computers and they developed a new mathematical framework that took a simulated quantum particles and placed them just outside a giant simulated black hole. And what they found is that the simulated black hole showed signs of quantum superposition. It validates lots of theories, one by scientists, mainly by scientist Jacob Bekenstein, who is a theoretical physicist, and he was a huge deal in the foundation of black hole thermodynamics, so how they emit heat and radiation and stuff like that. And he said that black holes can only have masses of certain values, and those values must fall within certain bands or ratios, like energy levels of an atom or quantized, right? There are certain packets, certain levels that they can be. And the work that Fu and et al. Did showed that the superimposed masses of those black holes did indeed fall into predetermined bands or ratios. So that mass was quantized, which was very interesting. Now to explain what that means. So black holes, right? We all know black holes. They are very big. And there's really two things about them, right? There's the singularity, right in what we believe to be the center, where all that mass and stuff is shoved. And then there's the event horizon. And that's kind of where the black hole, quote unquote, starts in a way, right? Like that's where once you pass it, no light can escape. And so the reason they looked at mass is because black holes are largely mass dependent, is what the term is. So the size of that event horizon and the size of the black hole will depend on the mass of the black hole, right? And that's what that equation is showing. We call that radius we call it a Schwarzschild radius. And that depends on 2 times a constant over the speed of light squared times the mass. And the mass is the mass of the black hole object of what you're looking at. And so if mass is the thing, really the only thing we can measure of a black hole, that's why they started to look at it. The key point that Fu et al. Used was one of Jacob Bekenstein's findings, because one of his key points was that the black hole horizon area, its event horizon, is an adiabatic invariant, which means that it stays approximately constant. It does not change when changes occur slowly. So that's like with the changes being possibly Hawking radiation or anything else going on. So if the event horizon is based on mass, and then its mass will stay approximately constant when changes occur slowly. It's has to stay the same, right? Something has to stay, and it happens to be mass. So that's what they looked at to measure. It's the one thing you can measure really with a black hole that won't change.
Okay, now, I wanted to jump in just about the superposition. You're about to get into this because you used this word and you kind of like flew right by what this means. And this is a really fun part of this. Like I find this really interesting. A superposition, even the word sounds really interesting as well. And it obviously connects to cats. And is this your cat here, Marley? What's going on?
Yeah, this is Emily Cat. There she is in a box. Yeah, that'll make sense in a moment. Some of you may be ahead of me. Superposition. So that is this, it describes the thing in quantum theory where subatomic particles, so very, very small particles, exist in multiple states. So they have, tall and broad or short and skinny, right? Until they interact with the external world. And the external world interaction is us measuring them, right? That is being measured or being observed. So the act of measuring it will throw it into one of its possible states. So the most common one is Schrodinger's cat. That's the one that people are most familiar with, right? Where you have a cat in a box and I don't know, there's like poison in the box or radiation hitting the box and the box is closed. And so you don't know if the cat is alive or dead until you open the box. And so the cat is both alive and also dead until you open the box and check, right? That's like the basis basic explanation of Schrodinger's cat,
Although
right?
I've heard a lot of physicists and astronomers like use like the more gentler, like alive or asleep. Maybe it's a bit morbid to say.
Oh, I don't know. Like, pretty sure Schrodinger said the cat was dead. I think that's
Well,
okay.
Schrodinger himself was a bit of a bad man himself. So
Yeah, it wasn't great.
yeah.
But yeah, I don't know. I've always heard the cat is dead. I've never heard cat is asleep. That's hilarious. Emily would not, yeah, she was so angry in this box. Like, I don't think she would be in any state but anger. But no, yeah, the cat, okay, is alive or sleeping, whichever one you want to go with, whatever, until you open the box and check it. So the cat is existing in multiple states. It's one and the other at the same time. You don't know until you open it. And so in quantum theory, the particle can be one state or the other. It's actually in both at the same time, and you only know which one it is when you measure it, right? When you measure it, it throws it into one of those possible states. And so Jacob Bekenstein was the first to give the idea that black holes may have a quantum property like this. They may have a quantum property since it's defined by its mass, and that mass doesn't change very much. And all of those reasons before that are very complicated that I didn't fully understand. But the research that they did was very, very exciting, the mass superposition in black holes, because they did find that in their simulated black holes with their simulated particles, that they, the black holes did have this quantum property, that they did have superposition in their mass. So they had multiple masses, like extreme heavy mass to no mass at all at the same time. And that was very exciting and very interesting to see, because I honestly did not really know that was something people were looking into. And when it came to black holes, trying to see if they could have that mass superposition in them. And the reason kind of for all of this really ties back to trying to get that general relativity and that quantum mechanics to work together, right? It's something that's been going on for a very long time because they're two separate schools of thought, and trying to bring them together is like very exciting and interesting. It try to tie together all of the theories that we have. Gravity we see, every day around us all the time, but still don't have a full extent of how it works on very big and very small scales, right? It gets a bit odd. So it was just a fun news story that I saw that I thought was very interesting. That's all I have to say about it, because I think if I try to say too much more, I will confuse myself.
Well, it's interesting. So you said like they've been trying to do this for a while, and you mentioned Hawking radiation. So obviously Hawking did a lot of this work in the 1970s. John Gregory on YouTube says this is too weird because back in the 60s, when he was in Signal Corp school in Fort Ord, California, there was a guy studying quantum mechanics in university. How old of a field is quantum mechanics?
Oh, it's old, like not like as old as time, but it's been going on. I think I've always heard about quantum mechanics. It's just whether or not, it sounds bad to say, but whether or not more money has been thrown at it, right, to grow the field, right? So it's been around for a pretty long time. I'm not sure if there's a specific person you can point to as to who did it, but the Schrodinger equation that came out in 1926, right? And he got the Nobel Prize in 1933. So it's been going on for quite some time.
Okay. And there's a reason why, and I think you even just alluded to it, why quantum seems to be being talked about a lot now. And you're reading this new study that's coming out recently, and there was just a big conference here in Vancouver that you and our special guest on November 17th, Rachel Wang, went to. So what's really going on there with this new attention? It is the money, but there must be something else going on as well.
Yeah. So from a science perspective, the conference was the quantum gravity conference, and that really tied into trying to explain gravity through the lens of quantum mechanics, right? Because our classical models start to fall apart. Even general relativity stopped working at some points, depending on who you ask, in terms of Hawking radiation, right? So I want to do a brief on Hawking radiation because that's going to come up. So that was Stephen Hawking. It was supported, this radiation, by general relativity and quantum mechanics, which was very exciting because now we have these two working together. And what it is it's a theory about how black holes, they act like black bodies, which are like the perfect perfect thing, radiating. And so the radiation from them was theorized to be released outside of the event horizon because of quantum relativistic and quantum effects. And so it worked. It would have caused, it had a lot of trickle down things, but his work worked for the time. It did work. It did lead to a paradox called the information paradox, which is if a black hole is evaporating, right, over time, you would only see the radiation left over. And Hawking's radiation would be the final radiation. And that was all you would see. It would lose all information about the initial state of that black hole, is that information paradox. So if you're losing all of that information, you'd only have the final state information. So the final state of about the total mass of the black hole, the electric charge, and angular momentum. But you would lose that about the initial state. And the problem is that many different initial states can lead to a final state, right? It can all go through some weird process and get to a final state. You can get from A to Z, but you can also get A, B, X, and Y to Z. And that was a problem because there's a core principle of classical and quantum mechanics, which is that here, in principle, the state of a system at one point in time should determine its value at any other point in time. So we should be able to work back from the final to the initial and find that initial state. And that was a paradox for a while, but it's now kind of a general consensus that we don't think that Hawking radiation violates it at all. It works fine in the quantum. They believe that it does lose information, but that information can be recovered. Instead, some people think that Hawking's use of general relativity wasn't quite right. So now you have this thing that we've used for so long, now not working quite right. Other people think that, maybe he did use it right and it's string theory that is wrong. There's lots of different things. But regardless of what went wrong with the original Hawking radiation equation, trying to find a solution to it and find a further solution to this paradox requires quantum mechanics and gravity working together, right? Neither one of them can do it alone. It has to work together. And that's where you get quantum gravity from. So Hawking's radiation and the information paradox is a good example of why they want these two to work together, but there are much other reasons too. Basically, the work that we've done in either field, there's still too many questions. And so if we put them together, maybe all of the questions about it would be answered. But it's kind of growing because it takes a lot of work and technology has to catch up with what we want to do as well.
Right. Interesting. And this information paradox, I've heard it being analogized, and I'm not sure if I'm confusing it with something else, but where you take an ice cube as its previous state, and then it ends up, maybe in a cup, and it melts, but then maybe it evaporates away into vapor. So you're taking like the vapor, and how do you know that it originally started as an ice cube?
Yeah.
And that being sort of like the paradox of, how do you get from A to B?
Yeah. Yeah, no, that's a good analogy for it. Yeah, how do you get to A to B? That information is lost. Yeah, and it's just not what we like to happen. It goes against one of our principles. It's very annoying. But now general consensus is that no, it's recoverable and it's fine if you do it with quantum mechanics. If you do it with general relativity, it's still a little murky, but also depending who you ask, because no one agrees on it, right? Like it's still an active field that's being looked at and developed. And because it draws from so many other fields of science, like string theory and all of this, that it becomes much more complicated the more you try to figure it out. But one of the ways to try to answer it would be using quantum gravity.
Yeah, no, this is really, really interesting. And, I'm glad that we're venturing into this, obviously as a public facing science center, like we planets and astronomy, like this is a very, very different field, like going into cosmology. This month is going to be our theme, and it does stretch my brain, which I like that feeling. I don't know if you like that feeling as well, where you run up against like your understanding, and then there's things that you don't quite understand, but you kind of do. And you just kind of like keep going along with the motions until you understand it a bit more, the more you get into it.
Yeah, I don't know if I like it, but it is nice to read about and be challenged. But it does become frustrating to like lack the language to explain it to people who may not have the same previous knowledge that I have. So that's the frustration. Is like I really want to be able to tell people about it, but it's very hard to explain this because it's so weird to think about, even to me. So.
Well, this is why we bring in other people. Like, you're not doing this alone. This is why we're going to bring in Rachel. And
shout out Rachel.
Absolutely. It's going to be a really fun night. and come on down. We're going to have a fantastic show. We're going to also be live streaming it as well. So if you just want to see that presentation online, you can get a ticket and get that presentation directly into your home. So go to our website, spacecenter.ca. And of course, that blog that I mentioned, you can go and read Marley's blog on our website, spacecenter.ca. And if you're here on YouTube, we've still got another 5 minutes. If there is any questions that you have on any of the stuff that we've talked about, of course, we talked about daylight saving times and mainly griping about it. The Chinese rocket that's tumbling to Earth today, maybe later today, and then as well as the Artemis rollout. Lots of fun stuff, Marley. So what are about this, as we get into cosmology, what are some of the things that you really get excited about? You say that you get frustrated with the explanation, but what are you really excited about when it comes to these topics?
Wow, I'm not a cosmologist.
No, I know you're not, but I know,
but it's hard to be. I am interested in parts of it. I do like, this is not to do with much of anything, but the theory of inflation and the problems with that. The universe, as we understand with the Big Bang model, is that it, started from a singularity, everything rushed out. I actually got a great question from a kid here the other day, and the question was, well, what caused the singularity? Like, what was before that? And I was like, the Big Bang model does not try to explain that. It just accepts that it's there and moves on. And so that part, what came before the singularity, is interesting. But also so is the part when everything rushes out and it grows so quickly, exponentially. It has to grow very quickly, very fast. And that period of inflation is very interesting. And that's kind of why I like the whole first galaxies, first stars mission of Webb, like when those would have first started, because it kind of helps us with the timeline of that inflation, how long that would have had to take, how long it would have gone for. Because you have, inflation period, dark ages, and then first light. So when was first light? And that can give us kind of a time, like a section of time where we can go back and be like, here's how long dark ages would have had to last, because we know when the CMB is, the cosmic microwave background, dark ages, first light, but everything pre-CMB, specifically that inflation period, I find very interesting.
Yeah, well, and speaking of JWST, Pride is wondering what that telescope is up to, and maybe in relation to this, is there anything happening with JWST in relation to first light?
Oh, when isn't there something happening with JWST? Let me look at their observation schedule, because you can see what it's looking at any given time on the Space Telescope Science Institute's website. And they have it for October, what is this? Okay, till October 31st till November 7th, I think, is what this is for now. And looking at it, we have solar system, clusters of galaxies. It looked at the Abell cluster, interstellar medium. Ooh, Crab Nebula. That'll be fun. Looking at a lot of stuff. Galaxies, clusters of galaxies. What's coming up? What day is it? The 3rd?
Mm-hmm.
Here we are, the 5th. Solar system, satellite. Oh, Webb's going to look at Titan, or at least trailing. TRAPPIST 1b. We talk about TRAPPIST a lot here. We talk about TRAPPIST. So we're going to look at TRAPPIST 1b, exoplanet systems, on November 5th about.
Cool.
So that's kind of what's up with Webb. I mean, Webb, things have to be visible in its field of view for it to look at, right? Yeah. So that's why there's 4 science targets, and that's why these things are so over the map. Solar system, star, galaxy clusters. Like, it looks at what it's available to see, depending on the what's been put forward and accepted as a proposal. So it's kind of up to everything all at once.
Great. One last question, which Pride might have answered for John Gregory. What math discipline is associated with the quantum stuff?
Oh God. What math? It feels like its own math. Like when I did quantum, like a lot of calculus, I think, as well. A lot of calculus, linear algebra, maybe. Like, it was a little bit of everything. A lot of math that I'm like not keen on redoing.
I'm laughing because Pride put, give us a miracle explanation, but then she also said calculus.
Yeah, calculus. Yeah, a lot of calc. I think I did linear algebra, a bit of it in quantum, but it doesn't look like it. Okay, so math stops having numbers after a certain point, and it just becomes letters. So it doesn't feel like math after that, but it is.
Awesome. Well, everyone out there in YouTube land, in Telesoptic land, in Facebook land as well, thank you all for joining us for another episode of Ask an Astronomer. We will be back here live in 2 weeks on November the 17th, the day of our event, but we'll be here live in the afternoon with another brand new show. Marley, thank you so much. We will see all of you in 2 weeks.
2 weeks. Come see Rachel talk about quantum gravity.
Bye now.